An example of a large-scale situation awareness application would be monitoring, for instance, activities in an airport. And in that situation, what we are trying to make sure is that normal activities are okay, but anything that is anomalous with respect to what we see in the environment has to result in triggers being sent to the appropriate software agents or even humans in terms of actions that they may need to take. And camera networks are becoming ubiquitous. For instance, in the city of London, there is on the order of 400,000 cameras that are deployed, blanketing the city. And the intent in such camera networks is to analyze the camera streams to detect for anomalous situations. When you have such a large number of sensors, the first thing that one has to worry about is overloading the infrastructure itself with the amount of data that is being continuously produced 24/7 from all of these sensors. That suggests that it is important to prune these sensor streams at the source in order to make sure that the infrastructure overload is avoided. And the traditional way to do surveillance is to have humans sitting in front of banks of monitors looking for any anomalous activity, for instance, in an airport. This obviously does not scale if you have on the order of 100,000 or 200,000 cameras blanketing a city, which is becoming fairly common in many large cities like New York, Chicago, London, and so on. And so cognitive overhead is another big thing that you have to worry about in large-scale situation awareness applications. And it is extremely important to avoid false positives and false negatives. By false positives, we are identifying events that are not really anomalous, but the system thinks that it is an anomalous event. That's a false positive. And similarly, false negative is saying, well, there is an event that took place that should have been caught but did not get caught. And that's a false negative. So both of these are very, very important metrics that one has to measure in large-scale situation awareness applications. From a programming model perspective, one of the important takeaways in just this discussion about large-scale situation awareness application is that the programming infrastructure has to facilitate the domain expert who is developing a large-scale situation awareness application to be able to deal with time-sensitive data. So what are the pain points in developing large-scale situation awareness applications? The first thing is providing the right level of abstractions, promoting ease of use. Simplicity is the key. Interfaces that allow seamless migration of computation between the edge of the network and the computational resources in a data center, for instance. Temporal ordering of events that are taking place in the distributed system. And propagating temporal causality. By that, what I mean is if an event, let's say, was captured by a camera at a particular point of time, it may be processed at a later point of time, in real time, but there's got to be a temporal causality for the time at which it was captured and the digest of information that was created. And such temporal causality is extremely important in the development of large-scale situation awareness applications. Another requirement in such large-scale situation awareness application is that there are live data that we are dealing with, but at the same time, we may also have to correlate that with historical data in order to make a high-level inference as to what's going on. For instance, if we see a speeding car at this point of time on the highway, we may want to ask the question, was this car involved in an incident in the last N days? And that is kind of historical data that has to be correlated with live data. So a programming infrastructure that provides facility for these kinds of things would make the life of the domain expert writing such large-scale situation awareness applications so much simpler.